Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about sigma notation in relation to sequences and series. Okay, so sigma notation, sigma is a Greek letter, typically means to sum some set of values. So we're going to give you the basics of sigma notation. So here's sigma, my drawing is sigma. And in the top part of the sigma, what you put at the top is the upper limit of summation. We'll go through an example of what the upper limit of summation is. And then the index of summation, which is going to be some letter, typically represented by an I or an N, but it doesn't matter what letter it is, as long as you're consistent with using that letter in the function. And then it's going to be equal to some lower limit of summation. Right? So sigma notation is represented by the Greek letter sigma. Index of summation can be represented by any letter, and the lower limit of summation does not have to begin with 1, although normally it does begin with 1. All right, so another example, or real example, is right. I'm summing a function where I have the input starting at 1 and the outputs ending at 6. So my index of summation is I, my lower limit of summation is 1, upper limit of summation is 6, and my function is 2i. So what this is asking you to do is to please provide the sum of the terms, which are the outputs, of the sequence which starts with 1, so the lower limit of summation, and ends with 6, upper limit of summation. You're going to use the rule 2i to convert the inputs, which are 1 through 6, to outputs. All right, so you're going to add 1 times 2, so 2 times 2 is 4, so 2, 4, 6, 8, 10, and 12 together. All right, so I have my students write this down and put this in their binders so they can reference this moving forward if they get stuck and trying to figure out what sigma notation means. But ultimately, it's just another way to represent a series for a sequence. All right, these are some formulas for special series. So I just put them in here as reference. We're not going to use any examples, but you might see these as you move on to higher levels of math. So this is lower limit of summation of 1, upper is n, and then for every input, you're going to add 1. So input 1, add 1, input 2, add 1, input 3, add 1, input 4, add 1. And so the sum of this value with an index of summation, a lower limit of summation equaling 1, is going to be equal to n. So the number of terms in the sequence is going to be the value for the sum. Sum of the first positive n integers, lower limit of 1, upper limit of n. Now you're going to add I for each value. So input 1, output 1, input 2, output 2, input 3, output 3, and you're going to add those together to n. And the formula for that is n times n plus 1 divided by 2. All right, and then finally for I squared, lower limit of summation 1, upper n, I squared would be 1 for input 2, output 4, 9, 16, 25, 36. And so your formula would be n times n plus 1 times 2n plus 1 over 6. So these are just standard formulas you can use when you're confronted with some sigma notation in series and you want to write in some function in relation to n as opposed to evaluating it term by term. All right, so other verbiage we need to review: expanding the series. So when we expand the series, what I'm looking for is for you to provide me with the outputs of the terms of the sequence based on the rule input, lower limit of summation, and upper limit of summation. So it would look like, in this case, input 2, output 10. So I'm expanding. 10 would be the first part of the expansion. Input 3, output 15, input 4, output 20, input 5, output 25, input 6, output 30. So these values here, 10, 15, 20, 25, and 30, would be the expansion of this sigma notation in the series. All right, so I want you to practice here. You can expand these series. I'll pause here for a moment. All right, so we get the expansion 5, 9, 13, 17, 21 for 4k minus 7, lower limit 3, upper limit 7. And then for the second one, 2 to the I, lower limit of -3. So again, it doesn't have to start with 1. Upper limit 3, 1/8, 1/4, 1/2, 1, 2, 4, and 8. Okay, next I want you to rewrite the series using sigma notation. So you're going to have to find a rule, find a lower limit of summation, which I'd like for you to use as 1 for now, and then upper limit of summation for 8, 12, 16. All right, so lower limit is 1, upper is 5, so I have 5 terms. My rule is 4i. So take the sum of the function 4i with an input starting value of 1 and an output ending value of 5, going up by 1 unit at a time. All right, do the same thing for these next 3 problems. All right, so you should get, for the first one, lower limit 1, upper limit 4, rule is 4n plus 1. Second one, lower limit 1, upper limit 6, rule is 2n, 2 to the n minus 1. And also you could start with 0 here if you wanted 0 to 5 instead of 1 to 6. And then the last one is lower limit 1, upper limit infinity. So these dots here say that it goes on indefinitely. And the rule is 1 over n squared, or you could say n to the -2. All right. So those are 2 options for you. Okay, that's it for this edition of Autumn Math. Thanks for joining us in our discussion about sigma notation. That's it for chapter 13. Hope you have a fabulous break until the next chapter and edition of Autumn Math.